Okay, so we will continue our discussion on slip flow for liquid, and we know that for liquids the no slip boundary conditions and no temperature jump boundary conditions are valid. So, no slip boundary condition for liquid, we can write that u at the wall will be equal to u fluid at the wall. So, velocity of the wall is velocity of the fluid at the wall. Similarly, T wall is temperature of the fluid at the wall. So, this is the no slip boundary condition for liquids. So, what does it mean? It means that our slip length in this case is 0, right. We can generalize, we can write delta u at the wall is Ls into delta u over delta y at the wall. This is the general equation for slip. Now, the slip length is very difficult to determine slip length by experiment. Okay. So, there are no experimental data available. However, people have tried to do molecular dynamics simulation to estimate slip length. Okay. So, the slip length has been determined using molecular dynamics simulation by Thomson and Thurian, and they have considered a case where the fluid flows through two parallel plates, okay, and one plate is moving. So, that is a equate flow situation, and they have found that the slip length is going to be a property of the fluid as well as property of the solid material. Okay. If you consider a case where the interatomic distance in the wall is of the same order as the distance between the molecules, then the slip length is going to be 0. Okay. Whereas, if the interatomic distance is about 4 times the distance between the molecules, then in that case the slip length could be as high as 16.8 times the intermolecular distance in the fluid. If you look at this table here, this term is representing the ratio between the interatomic distance to intermolecular distance. When this ratio is 1, the slip length is 0, okay, and when this ratio is becoming 4, the slip length could be as high as 16.8 times than the intermolecular distance in the fluid. Okay. So, that is what we learn from this molecular dynamics simulation data. Now, we know that the slip length is not a function of the shear rate or the strain rate when the value of strain rate is very low. Okay. So, the slip length remains constant for a pair of solid and liquid. Okay. However, it changes if the solid or the liquid changes. Okay. But this assumption that slip length is not a function of the strain rate or the shear rate breaks down at very large value of strain rates. Okay. So, in that case what will happen is the slip length Ls can be written as Ls 0 into 1 minus, this is the strain rate gamma dot over gamma dot critical into minus half. Okay. So, this is how the slip length is going to vary at high strain rates. Okay. When this is going to happen when the shear rate or the strain rate is higher than the gamma critical. Okay. So, this is the critical shear rate this is going to be the slip length at certain gamma, certain strain rate, and this is the slip length at low shear rates, so which is constant. Okay. Now here we talk about a critical shear rate or critical strain rate. Okay. It has been found that this critical shear rate at which the linear Navier boundary condition breaks down is low as compared to the shear rate at which Newtonian assumption break down. Okay. So earlier we had discussed that if the shear rate exceeds the twice the molecular interaction frequency, then the Newtonian assumption breaks down. Okay. Now here we talk about another critical shear rate at which the linear Navier boundary condition breaks down. So what we say here is that the critical shear rate at which Navier boundary condition breaks down is less than the critical strain rate at which the Newtonian assumption break down. Newtonian assumption breaks down. So typically this gamma c dot is about 0.3% of the strain rate at which Newtonian assumption would break down. Okay. So for example, if you have if you consider the same example where we have liquid argon between two parallel plates and one is fixed, the other if it is moving at about 3000 meter per second, then we would encounter a situation where the linear Navier boundary condition will breaks down. Okay. So and this velocity, although it sounds high, quite possible to achieve in micro scale flows. Okay. So if you have two parallel plates and one is stationary and the other is moving at 3000 meter per second, then here we would encounter a situation where the linear Navier boundary condition will break down. Okay. So here we are considering liquid argon as the fluid, right. Next we move on to talk about Reynolds number. Okay. How the transition occur from laminar flow to turbulent flow. So we talk about transition to turbulence. So the transition to turbulence can be defined using Reynolds number, which is rho u T over eta. Okay. So rho is the density, u is velocity, d is the flow length scale. Okay. And eta is the viscosity. So we know that for a pi flow situation, if Reynolds number is between 1000 to 1500, then the transitional flow starts to occur. Okay. So about 1000 the flow will be strictly laminar, between 1000 to 1500 the flow would try to exhibit a turbulent behavior. Okay. And if it exceeds 1500 or in some cases 2000, then flow become turbulent. Okay. So we know that if Reynolds number is less than 1500, the flow is strictly laminar, and if it is between between this is 1000 between 1000 to 1500 it starts to exhibit the transitional regime, and if it is greater than 1500, in some cases 2000, then it exhibits turbulent flow. However, so this is what happens in microscale tube flows or channel flows, okay. But in microscale, this critical Reynolds number or transitional Reynolds number is debatable. There have been some observations where the transition occur as low as few hundreds Reynolds number of few hundreds, okay. So this is quite debatable, okay. So transition of the order of few hundreds, okay. So RE of the order of few hundreds have been observed. So more work needs to be done, okay. So the Reynolds number at which transition would occur in microscale is not very clear, okay, and more work need to be done. Next we talk about low Reynolds number flows. As you know, in microchannel flows the Reynolds number is very less, okay. So that has an effect on how the behavior the flow is, okay, the nature of the flow. So we talk about low Reynolds number flow. Here we consider the length scale to be d and velocity scale to be u, okay, and we consider some scaling parameters to non dimensionalize the governing equations. So we consider x star as x over d, y star y over d, u I star is ui over u, and we define time star t star, which is the non dimensional time, as t divided by d over u, and we non dimensionalize pressure by p divided by eta u over d, okay. Now if you do inverse scaling, we get x equal to x star d, y star d, and you get ui as ui star, and t we get d over u into t star, and we get p as p star into eta u over d. Now if we use these non dimensional parameters in the conservation of mass and the momentum, we can bring the momentum equation to a form where Reynolds number and Froude's number emerge as two important non dimensional numbers. So if we put in mass conservation equation, the mass conservation equation will appear like this: del ui star over del xi will be 0, and the momentum equation will appear as rho into del ui star over del t star plus uj star del ui star over del xj star minus Fi is the body force into characteristic length scale divided by u square will be equal to minus del p star over del x star plus del square ui star over del xj star. So, this is this term is 1 over Froude number, okay, where Froude number is defined as inertia to body force or gravitational force. Okay. So, if you look at this equation, since we are non dimensionalizing this, each of these terms, okay, this term, this term, this term and that term, all these terms, okay, are of the order of 1. Okay. However, we have this Reynolds number appearing here. The Reynolds number and the Froude number are emerging as two important non dimensional parameters that would characterize the microscale flows. Now, in micro channel flows, as I said, the Reynolds number is very small, okay, so of the order of 0. Then, so in that case the entire left hand side will drop off, okay. So, microscale, the Reynolds number would tend to 0, okay. So, we will have an equation, so the entire left hand side will drop off. So, what we would have here is minus delta p star over delta x star, okay, equal to, or we can make it positive, del square ui star over del x j star square, there is a square here, okay. So, this is the equation that we would arrive at. So, now if the the pressure gradient increases by a factor a, then velocity at each point in the flow field will increase by a factor a, okay. So, this is a linear equation, this is a linear equation, easy to solve, and this is the nothing but the Poisson's equation, okay. So, if you solve this, you would see that as the pressure gradient increases by a factor a, velocity at each point in the flow field will be increasing by a factor a. So, what it means is that if you do an experiment at low Reynolds number and you obtain a flow field, you can increase the Reynolds number. Of course, we are talking about smaller, relatively smaller Reynolds number, which are close to 1. Then you can Reynolds, the experiment performed at 1 Reynolds number and you have obtained the flow field is applicable to predict the behavior of the flow at different Reynolds numbers, okay. So, this linear equation enables you to write that as Re is small and the pressure gradient and velocity are related using a constant. So, Reynolds number flow behavior remains same for different Reynolds numbers. Also, you can say that here in this equation you see that time does not appear as a term, okay. We do not have unsteady term here. So, that tells that these low Reynolds number flows are reversible in nature. For example, if you are considering flow occurring due to oscillation of a diaphragm, the nature of the flow that you see in the forward stroke of the diaphragm is going to be exactly reversed when the diaphragm goes in the backward stroke. Okay. So this is what we see, for example, in case of a piezoelectric micro pump. So the flows are exactly reversible. Okay. So T does not, this is time does not appear. So low RE flows are completely reversible. Okay. So those were two important conclusions of low Reynolds number flows. Next we talk about the entrance effect at micro scale. Okay. We talk about how the behavior of the fluid at a very entrance to the channel is appearing. So at macro scale you know that the flow is more or less uniform in both horizontal and vertical direction before it enters a flow situation, for example flow through a tube or a pipe. But in micro scale typically you have an inlet plenum, okay, and in micro channels the height of the plenum and the height of the channel are almost the same. So what happens is that the flow gets developed in the vertical direction, whereas in the other direction it is still developing. Okay. So because the flow gets developed in the vertical direction in microchannel as compared to microscale flows, the actual entrance length that we get in microchannel is less than what model would predict. Okay. So let us see here what is happening. So if you look at this plot here, okay, if you look at this plot, this is what happens in a typical macro channel flow situation, conventional fluid dynamics theory. You have a bigger entrance volume before it enters this macro scale flow channel, and where the the horizontal velocity and the vertical velocity profiles, they are uniform. Okay. If you compare that with a micro channel entrance, here we are talking about a plenum, okay, where this dimension is long as compared to the other dimension. Okay. So the vertical dimension is very small and the height of this plenum is equal to the height of this channel here. So that is the reason why the flow gets developed in the vertical direction, where in the horizontal direction it is still developing. Okay. So in typically in a micro channel we would see that when the flow comes from the inlet port and gets into the inlet plenum, which is typically a rounder shape, and then the flow gets into the micro channel, and these are typically of the order of few millimeter, and these are of the order of, let us say 50 to 100 micron, right. So the height here in this plenum and here in the channel area, they are the same, but if you look at the other direction, this is large as compared to here. So in this direction, in the horizontal plane the flow is uniform, whereas in the vertical plane the flow is developed. Okay. So that is the reason why the entrance length predicted by model is actually higher compared to what we actually measure experimentally. So if you want to theoretically predict what the entrance length would be, there are different correlations that are available. So one such correlation is entrance length LE is LE over DH is going to be 0.06 into Reynolds number based on the hydraulic diameter. Okay. So here this is valid for when Reynolds number is large, which is a case in micro scale flow situations. Now at micro scale our hydraulic diameter will be very small, and the Reynolds number based on the hydraulic diameter will be small. So what this equation would give is entrance length will be 0, but this is not what is observed. So this contradicts our experiment that have been performed, contradicts experiment. So the conclusion is that we cannot use this relation, and there have been different other correlations developed for predicting entrance length in microchannel. One such correlation has been developed by Sa and London, which tells that the entrance length Le over dH is 0.6 divided by 1 plus 0.035 into Re dH. Now here you could see if the Reynolds number goes to 0 as Re dH tends to 0, your entrance length will scale as 0.6 into dH. So this correlation can be used to predict the entrance length in microscale flow situation. However, it has been observed that the entrance length predicted by model, okay, or this correlation is about half the entrance length predicted from experiment. So if you look at this plot here, okay, this is an experiment which was performed at Purdue University for a channel of hydraulic diameter, dH of the channel was about 300 micron, and the height of the channel was 600 micron, and the Reynolds number was typically 1980. So in that condition this experiment was performed, and here we see that the entrance length that was predicted by the experiment is about 1.4 centimeter, okay. So this many micron, so this is about 1.4 centimeter, whereas the model that we see here, okay, this model predicts an entrance length Le from the model is about 3.6 centimeter, okay. So there is a difference between the entrance length predicted by the model and that is measured from the experiment. So the entrance length predicted by experiment is about half of what is predicted from the model. This has important consequence in micro heat exchangers and as well as in biomedical devices. For example, in micro heat exchangers we are talking about channel length typically in millimeter to centimeter. So the entrance length that is found experimentally or calculated from the model is not very different compared to the overall length of the channel, okay. And as you know that the heat transfer characteristics in the entrance region is different from that of the fully developed region. So it will have some consequence in case of micro heat exchanger design. If we talk about biomedical devices, as we know the shear stress that is found in entrance region is different as compared to that is found in the fully developed region. And for example, in one biomedical applications, for example, you are trying to bind one biomolecule to some antibody in the wall, in that case the shear stress that is acting on the molecule becomes very important, and as you know the shear stress will be different in entrance to fully developed. Knowing, understanding what exactly the entrance length is will affect the design of such a biomedical device. Okay. So this is where we move on to our next topic, where we talk about some solutions, exact solutions to some basic flow situations. So we talk about exact solution to basic flows. Okay. In microfluidics, in many situations we have long straight microchannels, okay, where the cross section does not change over the length. Okay. So here we will talk about few simple flow solutions. We will talk about quiet flow, partially flow, both steady, as well as we will take one case where the transient flow situation will be solved, and we will see how the solution evolves over time. But in such cases we will say that the flow is not accelerating in the direction. Okay. So the velocity remains constant along the flow direction. Okay. So what happens is the gradient of the velocity and the velocity component itself become orthogonal to each other. So the convective term in the Navier-Stokes equation drops off. Okay. So as a way to simplify the equations, we will say that the flow velocity remains constant along flow direction. So the velocity gradient and velocity become orthogonal to each other. So what it leads to is the convective term, okay, in Navier-Stokes equation drops. Okay. And we would assume here that the fluid is Newtonian, we would assume that it is isothermal, and in most of the flow situations we assume that the flow is steady, but we will also look at one or two transient flow situations, and we would say that the flow is fully developed in the range that we will be considering. So the first example we will take is the hydrostatic pressure, which will find for a fluid in mechanical equilibrium. Okay. So this is the simplest case possible, where we will try to derive how we can find out the hydrostatic pressure for a static liquid in a container, okay, from Navier-Stokes equation. Here the fluid is stationary, so the velocity will be 0, and the only terms that will exist is the pressure term and the body force term. Okay. So let us consider fluid present in a container, and we will say that G is acting in this direction and Z is in this direction, and here the fluid velocity is 0, and so the body force Fi is going to be minus G acting in the Z direction. So if we write down the governing equation, okay, the first is the velocity will be 0 everywhere. We say because we first the case that we consider is we are considering that the fluid is in mechanical equilibrium, that means the flow velocity at every point is going to vanish. If it does not, then the fluid will move and it will dissipate energy continuously because of the viscous interactions, and since it is in mechanical equilibrium and it is dissipating energy, that is not possible. So the velocity has to vanish, okay. And next we talk about the momentum equation, which is rho into del ui over del t plus uj del ui over del xj equal to rho fi minus del p over del xi plus del over del xi into eta del ui over del xj plus del uj over del xi. So that is the momentum equation. The velocity is 0, so all these terms will be 0, okay, these terms will be 0. So we are left with only the pressure and the body force term. So you can write delta p over del xi minus will be equal to rho zz minus, because the fi is minus zz. So if you integrate, you get p z will be minus rho into zz into z. So this is nothing but our hydrostatic pressure equation, where pressure varies linearly with the hydrostatic height. Now here we have made one important assumption. We have assumed that the density and the pressure, density does not change with the pressure, but actually pressure and density, they are related, okay. So if you consider variation in density, we can write that P over rho is P star over rho star. So P star and rho star are pressure and density at some known conditions. So at a known condition, let us say P star and rho star are pressure and density. So here this equation we can write as rho star divided by P star into P, okay, is the rho, okay, this is the term, okay, this is nothing but rho into gz, okay, minus of that is going to be delta p over delta z. So this is delta z. So we can solve p z will be equal to P star into exponential minus rho star divided by P star into g into z. So that is when you are considering variation in the density with the pressure, okay. So this is what you would arrive at. Now you can use this hydrostatic pressure equation to calculate what the height of the atmosphere is, okay, because the pressure condition at the sea level, and from there you can find what would be the height of the atmosphere that would lead to that much pressure, okay. For example, here you can say that P atmospheric, you know that is about 10 to the power 5 Pascal, right, and so P atmospheric is rho atmospheric into G into H. H is the height of the atmosphere, height of the atmosphere, and we say that let us say for example this does not change with H. Let us just try to scale it to see how the height of the atmospheric looks like. So 10 to the power 5 is going to be, this is about 1 kg per meter cube into 10 into H. So H is about 10 to the power 4 meter, okay. So this is about 10 kilometer, okay. So we can find out that the height of the atmosphere is about 10 kilometer. And next we consider a case where a thin layer of liquid is falling along an inclined plane. So we talk about a case where liquid will flow on an inclined plane. So here let us consider an inclined plane, something like this. Let us say this angle is alpha, and we say this direction here is x, and this direction is z. So we have a thin layer of fluid, okay, and the velocity will vary something like this. Let's at some point your velocity is u z, okay, and let us call this thickness to be h, okay, and we say the gravity is in this direction, okay. So we can write that u I is going to be a function of z, since we are talking about unidirectional flow here, and also there is no pressure gradient, the fluid flow is occurring because of gravity, so no pressure gradient. So that means the delta P over del xi is going to be 0. So if you talk about the Navier-Stokes equation, so rho del u over del t, del ui over del t plus u j del ui, u j del ui over del xj will be equal to rho f I plus del over del xi into eta del ui over del xj plus del uj over the del xi. So the convective term will be 0, because that is the assumption that we have made in the beginning. The steady flow, so this is going to be 0, and the body force F I is going to be G sin alpha, okay, G sin alpha, because it is going to be the in this direction, so it is going to be G sin alpha. So here your viscous term will have the gradient only in the z direction, so this will be del square u z over del z square, okay. So this is what this term would be, and Fi is going to be this. So you can write rho into G sin alpha plus del square u z over del z square will be equal to 0, right. So, sorry, you would have eta here missing. So, basically you would have viscous force coming in this direction and the body force coming in this direction. So, they are balancing each other. So, the boundary conditions, you can write the boundary conditions, one is u at 0, z equal to 0 is 0, that is the no slip boundary condition, and the other boundary condition is going to be, since we are talking about a free surface, this is a free surface, okay, this is a free surface. At the free surface the shear stress is going to vanish, okay. So, eta into del u over del z at h, at height z equal to h is going to be 0. So, this is no viscous stress at free surface, okay, no viscous stress at free surface. Now, if you apply these two boundary condition to this equation, you get this solution, u z is going to be sin alpha into rho z h square over 2 eta into 2 minus z over h into z over h. So, this is nothing but an equation of half parabola, okay, the equation of a parabola, and this satisfies the boundary conditions that the no slip boundary condition is satisfied. If you put z equal to 0, then the velocity is going to be 0, and when z equal to h, the gradient of the velocity is going to vanish, okay. So, the shear stress at the free surface is going to be 0. If you draw the velocity profile, so this is z, this is x along the flow direction in the inclined plane, and this is perpendicular to the inclined plane, and let us say we are talking about this as the film height, okay, this is the film height. So, the velocity is going to look like this, like a half parabola, and right at the surface it is going to be normal, okay. Here the gradient is going to vanish, the gradient is going to 0, and this is the general velocity, how it is going to vary along h. And a typical film of 100 micron thickness will have a velocity of the order of 1 centimeter per second. So, that is the type of velocity you can expect for thin liquid films. So, we stop here.